Welcome to e-learning. Today, guys, we're on section 6.2, the area between two curves. This is an easy extension of the way we solve the area under a single curve, as we're about to explain, and then we'll try a number of examples. Sometimes we'll find the region between two curves that don't intersect, and sometimes we'll find the area between two curves that do intersect. And sometimes we'll use the calculator to help solve the answer, and sometimes we will solve the entire problem by hand. Let's get started. So the problem today would be to examine a graph where I have two functions graphed. They may or may not intersect, or I may or may not use the region completely enclosed between where they intersect. And I wish to find the area of the, like what I see as the pink shaded region here. And a nice easy way to see this is think of it as using the area underneath both of the curves. So I'm going to grab my highlighter for a minute and take the yellow highlighter first and imagine that I was going to find the area from the function f of x between two values a and b all the way to the x-axis, and I'd be shading in this entire section right here. So I'll shade all that in. And I'll use the yellow pen. And the area, I'm going to call that area 1, would be defined or represented as the integral from a to b. The function is f of x dx. And that would give you the entire area shaded in yellow. Now remember, what we really want is the area that is between the two curves. So I see a nice way to solve that is to solve a second integral, which is the area of the region underneath the other function g of x. I'm going to shade that in green. And then I'm going to subtract. I'm going to call that area 2, which is also an integral from a to b. This time the integrand is g of x. And notice if I were to subtract that green area from the original large yellow, I would get the region in between. So I'm going to define here the area between is simply area 1 minus area 2, which would be the integral a to b of f minus the integral a to b of g. And now one of our properties of integration is if two integrals are being combined like this and the interval is the same for both, you can actually combine it into a single integrand. So our final way of writing this will be the integral from a to b, and the integrand could just be the difference of f of x and g of x. So this becomes our main definition or main technique for solving the area between two curves. Determine the little a, the little b, the interval. Sometimes that will just be given, like for example, if we want to use a subinterval between the 2 points of intersection, if there are points of intersection, or if there are no intersection points of the two curves, we just define an interval that we want to use. Sometimes we want to find the area of the entire region between the two intersecting curves. So like these two curves are going to intersect twice, and we could determine those intersection points and then just use those as the little a, little b. Either way, this is the way we have it defined. The area of the region between two curves, f of x and g of x. In this one, we're presuming that g of x is the lower function, or the one that's less than g of x. Then the integral is the integral from 0 to b, f of x minus g of x. Let's take a look at an example where the curves intersect and one where they don't. The first one I've actually got written out here. So this one I've gone ahead and I've also produced the figure that we're going to use, and I've already written out the process for this one so we can go a little bit quicker. The problem is to solve the area between the two curves. Functions are y equals x squared plus 2 and y equals the negative of x, and two vertical lines, x equals 0 and x equals 1. So I can observe in the picture that the graph y equals x squared plus 2 lies entirely above the function y equals negative x. So the terminology I use is that one of these is the upper function and one of these is the lower function. And we always want to subtract the higher number by the lower numbers. So it's always the upper function minus the lower function. So that makes my integrand x squared plus 2 minus the negative of x. So notice subtraction always is part of the integrand, and then it might be simplified to an addition if there's a negative sign in the leading term of this function. So I'm going to just clean that up and make the integrand x squared plus x plus 2. Notice I moved that x to the middle just because, put it in standard order now. We were given to use the interval 0, 1, or these two vertical lines define the boundaries. So it's the integral 0 to 1, x squared plus x plus 2. We're going to go ahead and solve this one completely by hand. So the antiderivative of our integrand is x cubed over 3 plus x squared over 2 plus 2x. It's from 0 to 1. And now plugging in 1 first, that's going to give us 1/3 plus 1/2 plus 2. Plugging in 0 is going to give us all zeros. So what's left to do is add up these three numbers. And 2 plus 1/2 plus 1/3 gives us 2 5/6. And since we have a picture, let's just take a look at it, see if it makes sense. The answer is just a little bit under 3. Well, I see 2 entirely filled in squares, so that gives us our 2. And if you look at the two partial squares, this one is exactly a half of 1. And then the one up here is pretty close to being a half of 1 also. The concavity here means it shows it's going to be a little bit under a half. So if I get 2 wholes and almost 2 halves, 2 other halves, that gives me a good idea that 2 5/6 seems to be a good answer. Our next example is where we only have the two functions given. So I went ahead and had the computer draw a graph for us. Two functions were 2 minus x squared and just y equals x. So we can tell the y equals x is going to be the line, and this other one is going to be this inverted parabola. Now this time the interval is not defined for us, so what we're going to have to do first is figure out where the two curves intersect. And in this one it's very easy to do to solve where they intersect by just solving the equation f of x equals g of x. Or actually I've got it written g of x equals f of x. To solve for the two x coordinates where the curves intersect. And depending on the functions, there might be more than 2 points. However, we're going to find that there's 2. So I've rearranged the equation into standard form by bringing all the terms to the one side. So it would leave me with the equation x squared plus x minus 2 equals 0. That can easily be factored and solved. And we get the two intersection points, x equals -2. X equals -1. Those are also visible in the graph. I'm just showing you that we can solve this also by hand also, which now gives us the domain for our integral. It's going to be the integral from -2 to 1, and then the f of x is the upper function and g of x is the lower function. So it's 2 minus x squared minus x. And if I remove the parentheses and put everything kind of in standard form, -x squared minus x plus 2 is going to be the integrand. Here's our antiderivative. And then I went ahead and computed the answer from here. Of course, we know we're going to plug in the 1 first, and then plug in -2, and then subtract the answers. But I got the answer 4.5, and if we do a quick inspection of the picture, 4 1/2 seems to be reasonable for what the area is here.